Alright, so this module is going to introduce you to a concept which we will use extensively throughout the course, and that is dealing with what is called numerical integration. Okay. So, we will start with a review of simple numerical integration, okay, something which is very familiar to you, you would have seen it in high school, undergrad, alright. We will proceed to the idea of interpolation of a function and use the idea, combine the first two ideas into more advanced ideas for numerical integration. Okay. So, that is going to be the flow in this module. We start with simple numerical integration, right. So, let us take a function f which has no analytical solution for its integral. Okay. We all know that there are these kinds of functions are there which cannot be integrated exactly, right. So, and what we want is the integral of this function. Okay. These kinds of integrals, they appear throughout electromagnetics, because the kinds of functions that appear in electromagnetics, you will have Bessel functions of various kinds, they do not have any closed form analytical expression. So, you are faced with this problem of how do I integrate. Okay. So, everyone knows intuitively the idea of Riemann integration that you studied earlier in high school probably. Its integration is area under the curve, right. So, if I draw it like this, if this is say A and this is say B over here, then the area under this curve is what is the integral of a to b f x dx. Okay. Now, you would have also encountered simple rules of integration in your schooling, which are about how to do this integration approximately, right. So, the first rule of course is the what is called as the rectangle rule, it is called, or the midpoint rule, that if I have some function over here and this is my interval a comma b and this is f of x, then what does it say? If this gap between a and b I denote as h, I replace this by one single value over here, right. So, that is the midpoint, right, f of a plus b by 2, and approximate this integral by what? By the area of this rectangle, right. So, it is, so that is my the length into width, right. Hopefully, everyone has seen this before. This is as simple as it gets. So, you can, this is also called a staircase approximation of the function, right. So, as you can imagine, this will not be very accurate. To make it very accurate, what do I need to do? Make h very small, right. That is one way of doing it. The second rule which you would have seen would be called the trapezoidal rule. Let us take the same function over here, try to draw it again in the same way. So, if this is, let us say, the 2 points a and b, what does it do is says, okay, instead of putting a rectangle through the midpoint, let me put a trapezium that covers this, right. So, it is going to take a trapezium like this and estimate the area as this quantity over here. Okay. And you can see f of a is going to give me this length, f of b is going to give me this length, and this is the formula for the area of a trapezoid, right, half of h into the sum of these two quantities. Okay. Obviously, we expect this to be more accurate than the midpoint rule, okay, because instead of a flat thing, I am fitting a linear function over here. Okay. If you wanted to get an even more accurate answer for the same integral, the next step logically you can see this was order 0, this is order 1, order 2 means what is the kind of curve that I will fit? Here I fit this dotted line was a polynomial of what order? This dotted line, this dashed line over here, this is a polynomial of order 1, straight line is polynomial of order 1. In this case, this is order 0, this is order 1. So, stands to reason the next step to take is, okay, let us fit a parabola through this function, right. So, let us say this is my a, this is my b, okay. So, I can take some 3 points like this over here, and what this rule will try to do is, okay, let me somehow fit a parabola through these 3 points, because I need 3 points to uniquely specify a parabola, right? And then compute the area. Any polynomial function, the advantage is that what about its integral? I can integrate a polynomial in closed form, right? So doing that gives me all of these rules, right? So back in the day when it was innovative, people's names went behind it. So some person by the name of Simpson discovered this rule. I mean, if you were born 300 years ago, it would have been named after you, right? There's nothing very great about it. But this Simpson's rule tells you, gives you an expression which is accurate to order second order. So as I go to higher and higher orders, I will be able to better approximate the function. And once I approximate the function, integrating a polynomial is easy. Okay. So that's the idea behind simple numerical integration. Let's move a little bit ahead with this. Let's try to find out what is the underlying idea behind these simple rules that we have seen. Okay. So what is the basis of these simple rules? Not surprisingly, the Taylor's theorem comes of use over here. We have used this extensively in numerical techniques and whatnot, right? So this tells you that a function f can be approximated about a point x naught in terms of, let's increasing orders. So the first term is constant f of x naught, then I have a linear term, and then I have quadratic term, and so on, right? And it's an infinite summation. Okay. So let's take let's just try to make the math simple. Okay. So let's just set x naught equal to 0. Okay. So what is f of x then? So f of 0 plus x f prime plus x square by 2 f double prime, and so on. Okay. I can put the origin wherever I want. So I've just put x naught at 0 just to make the math easy. Okay. So now I have a sort of an analytical form for f, which is an approximation. It will be an approximation depending on how many terms of this series I keep. Okay. Now I want to integrate this. So if I integrate this, what will happen? I am going to put this inside over here. So the first term, what happens to the first term? It's a constant, right? Integrating from 0 to h. So integral from 0 to h will simply give me a h, right? So this will give me a h. F naught is a constant. That's the first term. Then the second term is integral of x dx, right? So I'm going to get a x squared by 2, 0 to h, and f prime is a constant. Okay, it's f prime at, when I say f prime, what am I saying? I am saying f prime at x naught, which is equal to f prime at 0. So that's a constant, right? And the next term is going to give me x squared by 2 integrated once will give me x cube by 6, 0 to h, and I will have f double hat. So this is again very simple to do. All these higher order terms. Okay. So now you can see where these simple rules that we have seen, where do they come from? So the rectangle rule that we saw earlier, what did it say? It kept it, it replaced the function over here, it replaced the function by a constant value, right? So in this term, if I keep only the constant term, what will I get? Rectangle rule will tell me that this integral over here, let's call this I, will say I is equal to h of f naught. Okay, and plus the error. What is the order of the error? Squared, right? H squared f prime, this is the order of the error, right? So that's the so you have got the value of a function at one point multiplied by the interval. That's your rectangle rule. Okay. So now when I go to trapezoidal rule, what am I going to do? I want to keep linear, right? But dealing with linear terms now, I have to somehow do something about this f prime. So how do you think I should replace f prime by? Right, finite difference, right? So I can say that f prime at 0, I can write it as roughly what? f of h minus f of 0 divided by h. Okay. So, if I keep the first two terms, I will get f naught plus h square by 2 f of h minus f of 0 by h, and the error is going to be order of h cube f double prime. Okay. So, this thing will simplify, one h will get cancelled. What am I going to get? I will get, so h I can take common. What is the coefficient of f naught? Half. And what is the coefficient of f h? Half, right. So, I can take that 2 outside. I am going to get f of 0 plus f of h plus order h cube f double prime. So, does not this look exactly like your trapezoidal rule, right? So, you notice that this is based, the underlying principle is Taylor's theorem. You can keep going to higher and higher terms, you will get more and more accurate expressions. Okay. So, these formulae after Simpson they stopped being named after anyone because it became too boring, but this general set of principles they are called Newton-Cotes formulae. Okay. Just something to know, does not really matter over here. So, what I wanted to convey in this particular module is the basis behind numerical integration, simple numerical integration. Okay. As we go further, we will look at little bit more complicated ideas. Okay. Okay. So, we were looking at numerical integration, right, and we found out that the basis of the simple integration rules that we came across in high school, like the rectangle rule, trapezoidal rule, etc., it was basically Taylor's theorem. We want to extend this idea and sort of formalize it a little bit more. So, let us just do that. So, what we saw was the trapezoidal rule was for an integral from 0 to h, everyone is familiar by now, h by 2, and the length from at 0 and the length at h, right. So, this was my function over here, this is 0 and h, right, and this is my f of 0 and f of h. And what this approximation is doing is it is putting a straight line like this and telling you the area over here, right, that is what is computed over here. But this was for one interval only from 0 to h. Now, I want to basically just extend this rule over an entire interval. Okay. So, let us say I have n points x1 through xn, right. So, this is my x axis over here and I have x1, x2 dot 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 up all the way up to xn, and let us assume that the spacing is uniform, although it need not be. Okay. So, if I want to just apply this trapezoidal rule to find out the whole integral from x1 to xn, I just have to add the contribution for each of these segments, correct. So, if I want this over here, so I can say this is equal to, what do you think it will be? So, for the first segment over here, right. So, h by 2 will come and I will get f of x1, then I will come to x2, I will get f of x2 with, and its coefficient will be
1 by 2.
So, its coefficient will be h by 2 from this interval. Similarly, there is a x3 over here. When I take the contribution from this interval, x2 will come again. So, its contribution will be another h by 2, right. So, this whole thing I can write as, so I can take an h common, I will get, so 1 by 2 f of x1 plus f of x2, and finally, the last term will be a half of f of xn, right, pretty straightforward. Now, we could have stopped right here if this is all we wanted to do, we could have stopped here, but let's try to write it in a more standard way. And what is that standard way? Let's write this like this, a summation, okay, I is equal to 1 to n f of x I multiplied by some w I. This formula fits into this mold, right, and you can see the w i's are pretty straightforward. W I is equal to h by 2 for 1 and n, and for others it is just h, right. So, w I is equal to h by 2, I is equal to 1 and n and h else. Okay. So, we did not do anything new, we just rewrote what we already had in a little bit more what I am going to call the standard notation. So, this is the approximation of x1 to xn f x dx. Okay. Now, this way of writing it might look a little strange, but this is what we call a quadrature rule. Now, what are the ingredients of a quadrature rule? It is the case where I do not know the analytical integral of an equation. Okay, that is the first thing. I do not know how to integrate my function analytically, that is why I am doing all of this circus. So, instead a formula tells me an approximation of the integral. What is this formula? So, a quadrature rule means a formula. Okay. So, the word quadrature rule sounds fancy, but what is it? It is a formula. What are the two ingredients of the formula? Weights, so w I, and the points at which this function should be evaluated, xi. Okay. So, once I tell you that here is a quadrature rule, you should ask me what are the weights, what are the function evaluation points. These evaluation points are also sometimes called nodes. Okay. And once that is specified, now supposing you had this function f of x. Now supposing I tell you, okay, now I want to integrate some other function g of x. So will I have to change the quadrature rule? No, I have invented, after a lot of hard work, I have invented a quadrature rule. Okay, and I use it to integrate f of x. Now you come along tomorrow and say, no, I want to integrate g of x, where g is some different function. Do I need to change the quadrature rule? Answer is yes, answer is no. Any other answers? Objective is to integrate the function. Do I need to change the quadrature rule? So, to answer that, you should ask me what is the quadrature rule? We just discussed. What is the quadrature rule?
Depends upon the function, right? Because the points.
Okay.
Because then we need g of x2, because we decided each point by the mode of the function, right? Because something looks like a trapezoid, then we have to take that section to the x.
No, not really. What we did is we took the line over here, the x axis, we chopped it up at uniform points x1, x2, x3 up to xn. Okay, and the price I am paying is that I am going to say in each segment x1 to x2, x2 to x3, I am going to approximate by a trapezoid, whether or not it is a good approximation or not. So, if I come up with a new function g, I do not have to change the quadrature rule. I am given xi and wi, these are fixed. So, how will the integral of this new function g come? It will simply be, so if I want integral now g x dx over the same interval x1 to xn, I just change the value of the function, right. So, I is equal to 1 to n g of xi wi. I already knew xi, I knew wi, so I have to just find out the value of the function. So, you see how much of a power this is. I do not need to know the analytical integral of any function, I just need function values. Knowing the value of the function at a few discrete points, I am able to approximate the integral. That is why this so called quadrature rule is so useful. You make it once, you can use it for any number of functions under certain conditions, and we will talk about those conditions as we go along. Okay. That is why this quadrature rule is very important, useful rather. Okay. Now, so you noticed one thing, that what we were doing so far is, for example, this was trapezoidal rule. We could as well have made a quadrature rule out of Simpson's rule. Simpson's rule, what did it do? It fit a parabola in between each segment, right, and then that approximation will of course be better, right. So, now you can think, okay, how can we make this more accurate? Okay. We want more accuracy for the same number of function evaluations. Now it seems that if I want more and more accuracy, then I should evaluate my function at more points, right. For the if I want to fit a parabola, I need more points than if I want to fit a line, right. Now, so the question is, you can be greedy and you can ask, can I get better accuracy while still retaining the same number of points? So that's what we are going to investigate. Okay. So